Dear ladies and gentlemen, welcome to our webinar, LVRSys, the solution for voltage stability problems, issues in industrial facilities. To briefly introduce myself, my name is Stefan Hoppert. I'm Managing Director at Ebele Nürnberg. And today I'm also a speaker because 12, 13 years ago I joined Ebele exactly with this issue, with the issue LVRSys, with my master thesis, and I also take over to Thomas Schwarz.
Hello, also from my side, my name is Thomas Schwarz. I'm now working for Ebele since 9 years on the low voltage regulation LVRSys project. And we are happy to tell you today about what can make our solution for the industrial facilities and grids and how we can improve it for the future.
So just for your information, by participating today's webinar, and if you are using the chat functionality, the name of the chat couldn't be seen from everybody. So just to give you the hint. So after this formalism, so have fun with the product presentation now. So just to go through the agenda. So I want to start with new challenges for the low voltage grid, because the low voltage grid and the industrial customers, they are really combined together. So that means if we have influences on the low voltage grid because of new issues, then it would affect also the industrial customers. So voltage regulation to increase energy efficiency and service life of the electrical equipment will be the next point. So I introduce the first step, the system, and also combine then the utilities to industrial customers. And Thomas later on in this presentation will explain how to reduce voltage dip surges and also increase the availability of the electrical equipment. So just to go really fast through. So we have worldwide goals in almost each country in the world, so that global carbon emissions must be reduced. So must be reduced a lot. And I don't want to get in detail with the graphic. I don't want to explain it. So when we are going according to the goals, then it means that we have to really build up a lot of renewable energy suppliers, like photovoltaic, like wind turbines, or like different renewable energy sources. It means also that the mobility have to be a huge electrification of the mobility, and also the heating sector. The heating sector, the last point, also a huge electrification will be taking place if we meet the goals. So what does it mean for the PV worldwide? So just really to go fast through the last year, so seen on the graphic left, you see 2022 and 2023, the increase amount of photovoltaic inverters and plants is about 38% in the last year, and this year is even expected that the photovoltaic will increase by 53% just a year. So if you go to the right graphic, you see it's a worldwide issue. The biggest player here is China. China with almost 150 gigawatts only in the year 2023. And also India is a huge upcoming market with 17 gigawatts this year. In Europe is Germany and Spain especially. And also in America, the United States with over 40 gigawatt and a growth rate about over 100%, a really huge number. So the photovoltaic topic is coming up very fast worldwide. What about electric mobility? Electric mobility is also increasing all over the world. So here mainly driven from China. And you see in 2023, we will reach about more than 12 million electric vehicle sales. And here you can see it mostly driven by China. Also, a second point is Europe, United States, and the rest of the world is expected to increase very fast when the prices for batteries for the engines will go down. But if the market will scale up, and it's of course expected and the price will go down. And if we are thinking about the total number of vehicles worldwide, it's more than 1 billion. So at the moment we are with a percentage ratio of electric vehicles about just 1%. So it means there is a really huge potential to grow. Heat pumps. You can see it. I explained the first bar in green. The first bar in green shows you that the heat pump market increases about 10% a year. In Europe, the market is increasing more because of the situation with Russia and Ukraine, and the most European countries want to be independent from Russian gas. And here also, it's most common that the heating will be done then by heat pumps. Heat pumps is a story also worldwide, in Europe, United States, China, and also in the rest of the world. So what does it mean? What does it mean to distribution grids? To distribution grids, if you take a look to the news, you can read it very often, also worldwide, that there is a huge effect on the distribution grids. And just to give an example here, what I have read this morning, so Greece power grid is in risk of blackouts amid high renewable share demand drop, or also growing demands puts the EU electricity grid under pressure. So it means all the new topics which are coming up the next years, the next decades, the next centuries, it's of course a topic for the distribution grid. So what does it mean? What does it mean to all of the grid levels? So not only for the distribution grids, also for the medium voltage grids, for the high voltage grids, and for the highest voltage grids, there would be more and more voltage fluctuations in all of these levels. And what does it mean? And also we, as the manufacturer of the low voltage regulation system, we were really at this time, 12 years ago, we did not expect this kind of voltage curves we saw. And you can see it here. It was of our first pilot project in Germany 12 years ago. And we have seen a voltage fluctuation and also a huge unbalance in the voltage characteristic. And what did the utilities always, or what they have always done? They use the conventional measures in the distribution grid, so with reinforcement and expansion of lines and local power stations. And what does it mean for the industrial grids, and what's the impact on the industrial grids? Of course, up to this point, I just spoke about the impacts on the grids for utility grids. But of course, that industrial customers are connected directly to the grid, to the utilities, and the utilities then, for them it's allowed to supply industrial customers with plus minus 10% of the nominal voltage. So that's a standard EN 5160, and of course we know that's an European standard. This European standard is also fulfilled worldwide, we know, but in a lot of countries, in many countries, we have the situation that's not just plus minus 10% is the case. So we have very often the situation that plus minus 20% is the case. And that means that it has a huge impact on industrial customers and also households. So there will be a lot of negative impacts on the electrical loads in terms of the energy efficiency, and also a lot of negative impacts on the electrical loads in the terms of lifetime, of service life. You can expect if the voltage is plus 15% over the nominal voltage, so for example to 260 volts, what is the influence then to lights or to engines and something? Why we are now going for industry customers? Because in the past we designed the product especially for the grid operators. So means the product is mainly it's a best product for utilities. So we did the development to the requirements of utilities. But then we found out with a lot of contacts for industrial customers that the goals and the requirements are more or less the same. So means for the grid operators, the most important point were no maintenance. Also, it should be maximum service lifetime availability, and it should absolutely highest in the efficiency, energy efficiency, and no feedbacks to the mains, so no power quality effects when the system is installed. And with the contacts for industrial customers, for them it was absolute necessary that we are the lowest in the investment costs. So of course I can say we are not the cheapest here with this kind of system, but compared with the OPEX, with the operating cost, because due to our high efficiency rate and no service life, no maintenance costs, we saw that we have, compared to competitors, a lot of advantages, and the advantages are so great that the disadvantages of the higher investment costs are overcompensated to the most of compared to the most of competitors after 2 years. And if we are calculating like that, it is an issue absolutely also for industrial customers. So just to compare with competitors, so not to compare with names, just to compare with technologies. So we see there are a lot of systems existing in the market with series transformers and converters, like the right picture here, or with series transformers and motor drives, like the first picture on the left side, or with series transformers and converters in the middle side, so with a intermediate circuit. And also there are systems with integrated energy storage, capacitors, accumulators, but these are more or less UPS devices. And of course, we are not comparable with UPS devices at this point. So when we competing and comparing us to this kind of technologies, so we see due to our principle, our power loss, just for a principle, our power loss is half of them. So it's half of the competitors. The reason is that we have the transformers just in the mains, so in series with the main line. So not we do not control a transformer which control a transformer, so we control directed transformers in the mains. And that means the power losses is more than half than compared to competitors. And this kind of principle is really robust and with a long lifetime period. But at this point, I have to say it's a really good solution for voltage fluctuation, for voltage stability, but we also do have limited influence on voltage dips and compensation. So voltage dips, I know that is a huge topic for industry customers, but here we have to say at this point we have a limited influence. I will make an example. But just before I make this kind of example, I introduce you to the operation principle, what the system is doing. So it's easy explained. The system takes the left unbalanced and fluctuating voltage and brings it to the right voltage according to a reference value in tolerance limits. So tolerance limits are, and also the set point is adjustable because these are parameters, and that's the job of the system. The system brings it back to a really soft and good voltage range which can be adjusted. Jumping to the influence of voltage dips. Of course, our system has a control speed of 15 to 25 milliseconds. But what does it mean to voltage dips? So because of the principle, and I jump to the calculation on the right side, the output voltage is dependent from the input voltage, and then we can regulate and add the input voltage in a percentage step. That means if we are talking about a system which could higher the voltage by 20%, we have to multiply this 20% with the input voltage. And that means if we go to the right table, if the incoming voltage, the UN, the nominal voltage, is going down to 70%, multiply with 20%, means multiply with 1.2, we can reach an output voltage to 84%. If the voltage is going down to 75%, we can reach with our 20% system an output voltage of 90%. So 90% means then we are back to the limits. So we are back in the tolerance limits plus minus 10%. That means with a 20% system, we can mitigate this voltage dip and bring it back to the limits. But here you can see if the voltage dip will go down to 50% and we higher it by 20%, then the rest of the voltage will be 60%. So the less the input voltage is, the less the effects on the voltage dips to solve it through our system. System is made for the voltage fluctuations, but if your dips are not going deeper than 75%, of course, then we can help. How does our systems look like? So with different kind of cabinets, depends on the size of power. So means the cabinet size, one here on the left side, it's up to 110 kVA. So means we have, it's a really small cabinet, 60 centimeters wide, 60 centimeters depth, and 180 centimeters high. And of course, if we go bigger, so then we have a 200 centimeter high cabinet. And if we go even bigger, then we have a 220 centimeter high cabinet up to 630 kVA. And when we go to our biggest cabinets, we use more than just one cabinet. Then we have to bring each phase in a different cabinet, and then we use 3 cabinets up to 1600 kVA. And our biggest system at the moment we built up is a 2000 kVA system, and here we have 4 cabinets with 1 meter 20 in the weight. And here, of course, with this kind of huge systems, we are not using NH separators, NH switch disconnectors. We are using direct bus bar connection. So you can see it on the right picture. It's a really it's a huge bus bar connection. Transformers are direct in the back of the cabinet because of heating issues, and it's easy and secure and safe construction then. So I explained up to now the principle from the beginning, and now I want to hand over to Thomas. Thomas will explain you how to install the system and gives you also some examples what we did with the system for industrial customers up to now. And of course, at the end, because then at the moment we are at the beginning with industry customers, but we also looking forward to know cases, industry cases, also from your side, what we can do for you, because system is developed for utilities and for a lot of applications for industry customers, but we know we can do even more.
Thank you, Stefan. So for the installation of the systems, on the left side we see our cabinet, and short explanation to the points where we are. Here on the upper part is the regulation of our system, and the connection will be made on the lower side with some clamps here and here. The input side on the left side and the output on the right side. So it should be from our side. Our target is to make it as easy as possible. So you enter in the cabinet from below, and you connect the cables direct on the clamps on the input side, and you connect the cables on the output side. That's all you have to do after you installed the cabinet on the proper position. Then you switch the system on and it's working. Here on the drawing, you see it again. It's coming the cable from the line where the distribution transformer is connected. Here is your connection point to the grid, and then it's connected to the clamps here on the input and here on the output side. That's it. So for us, it's necessary that it's easy to install, and you don't have to do a lot of things afterwards, the installation. Here we see some pictures from how the installation is made. On site, we have seen a good example how to move the cabinet. This is a small wagon where you have to remove the wooden pallet before, and then you can put it on the wagon, and then you have not a lot of height, so you can go almost through all the doors. So if the cabinet is 2 meters high, then this will make maybe 2 centimeters more, so you can easily go through a normal door. And here we see the cabinet on the second picture as it is in the open space, and here when it's closed, so it looks like a normal indoor cabinet. And as Stefan said, the transformers are on the back side. So here we see the 3 phases. So for each phase we have 2 transformers, the bigger one on the bottom and the smaller one on the top. And this will be always on the back side. So from the front, it's not visible for you, and also for the service, or it's not necessary to see it. And it's also good for the heating, that the heat which is coming from the transformer is on the other side of the system. So this makes it easy for installation, so you have no contact with the transformers. For the regulation principle, it's here to see the blue line shows the voltage. When it's fluctuating, it's going up above the tolerance band. So we want to make it as simple as possible. So if it's above the tolerance band, then we step down. If it's below the tolerance band, we step up. So these 2 ways are possible. And for the regulation speed or regulation time, how long it takes till it steps, this is a parameter you can set. And here, if it's 1 volt for 1 second, so you multiply it, and then you get the regulation speed for 1 volt seconds. So it should be quite simple. And normally with the regulation parameters, you don't have to set anything. The standard parameters works quite good for most of the applications. So now we want to show you some applications we have made in the past. So for the energy efficiency for industrial customers, all the equipments in the industry are mainly connected with 3-phase voltage. And through the automation, we get a lot less of handwork in the factories. So all is made from electrical power. And if we see here, there are different machines, and they are all connected, and they are working the best at their voltage level which they are designed for. Here you can see the voltage. The upper line shows the 230 volts, which is the nominal voltage here in the EU. And the lower line shows the average voltage in this case where it was. So it was 215 volts, which is, yeah, I think it happens in a lot of grids that you get in the end of the line, you get a reduced voltage, especially if you have just big loads connected, which will drop the voltage, and then you get this voltage. The devices are designed for are working most efficient with 230 volts. For example, all inverter-driven machines are working the best with 230 volts or even a bit higher. Some other devices, because there are some people in the field who say, okay, you can save energy if you reduce the voltage. This can happen for some devices. For other devices, it doesn't work or it makes it worse. So for us, we don't want to sell you the system as an energy saving system, but out of our experience, it makes more sense to have it on the nominal voltage, because then all the devices working proper and more efficient than if the voltage is too low or far too high. With our regulator, we can make it that you get a stable voltage around 230 volts. Here an example which you maybe can consider if you think about the costs. So it's about the cable reduction. On the left side we have the graph which shows you two lines. The green line is for the 215 volts. It shows you if you have a stable power load which is connected to this 150 square millimeter cable with 120 kV. On one side, it's connected with 215 volts, and the other side, it's with 230 volts. The difference of the voltage considers that in the end, you get a different current. So if with a higher current, with a higher voltage, you get a smaller current, and with a lower voltage, you get a higher current. And the current is the most important for the cable losses. And therefore, if you have a higher voltage, you can save money because you have less losses. So in this case, we have the example that we installed our system, and the orange line below shows you the difference from the beginning on the length of the cable. So at 150 meters, you see the break-even point, because the purple line below shows you the losses we have through our LVRSys, which are quite less because the efficiency is 99.7%. So, but if you consider how many meters you have in your fabric from the station where you connect till the end, so from this point on, you can even save money if you have longer lines and you boost your voltage up to 230. So on the right side, we see here a short calculation example. Then if you have more than 100, if you have 180 meters and it works for 10 days, 10 hours per day, 255 days a year, and you have a power cost of 0.3 kilowatt, then you can save each day 230 euros, or per year it's about 60,000 euros. This sounds quite a lot, and it should idea how much you can improve your efficiency of the total devices. And besides this, if you have a proper voltage, you even save money if your cable length in the whole factory is quite long. The next example is from our project in Kenya. There we have installed a 630 kVA system in a mill. It's quite big mill where they grind corn, and they have large engines and mills which had always problems. So they had voltage problems because the input voltage was not stable. Their machines got broken, or they even stopped working. So they asked us if we have a solution, and then we installed this LVRSys. Here in the picture you can see how it looks before and after. On the upper lines you see the input voltage, which is quite high. So it goes up to more than 250 volts. And this is the input voltage. On the lower side, you see the regulated voltage. So this comes, we can make both in one graph. And it's at the same time. You see here, it's regulated more or less 10% down. And that's, for the factory, it's good. And besides this, the three phases are important that they are symmetric. If you see here on between the phase L1, the pink line, and the L2 are 9 volts difference. This makes a big problem for engines like mills, all three-phase engines. They have problems if they have unsymmetric amplitudes of the voltage. And with our regulator, we can stabilize this because it's possible to regulate each phase separate. So in the end, we solved the problem with our system. The customer said they have far less maintenance costs. They have not a lot stops in the production, and the motors are working quite fine. The lifetime of all the equipment is going higher, and the stability due to the stable voltage is far higher, because you can imagine if the voltage is too low and you regulate it to a higher level, even if it's a short dip or it's going down a bit, it's still on a higher level, that it's constant and stable and supplies you for a longer time. So this was another example we have, is overvoltage protection for wind power. So it's also an industrial application. You see the windmills, they have also own consumption. And here in Europe, we have a norm which says that you have to supply your own equipment with their own supply and make sure that they don't get destroyed from overvoltage. That's why a big wind company came to us and said if we could help them with this problem. And here you can see the white line, which is going up here, shows the voltage on the input side, which goes up to 120%. And the output on the pink line, purple line, shows you the output, which is regulated through the LVRSys. And within 30 milliseconds, we can regulate the voltage down for more or less 20%. So the voltage goes up, our system regulates it down and protects, therefore, all the devices of their own supply. This, is quite special design for this company, but it shows you that it's also possible to have it as an additional overvoltage protection with short-term reaction times. And here is the VDE. It's a German regulation. It's made that there is allowed to have for 130% of the nominal voltage just for 100 milliseconds. And with our system, we regulated it within 30 milliseconds, so we could solve this problem. And even in steady, if it's a steady state operation, then the voltage is regulated and all the devices have a longer lifetime. The last example is voltage stability. So here we had Autobahn, the German highway. There is some service toilets and different things which are supplied from a long line. On the upper picture, you see the red line shows you the cable which is lying there. It's about 2 kilometers away. So if you can imagine, you have a long line, you have a big voltage drop, and in the down yard of this house are big pumps to be supplied, and they had a lot of problems that the pumps are not working well because they see undervoltage issues if they start working. Here you can see how it looks like. The voltage on the upper line, the nominal voltage was here 220 volts because the voltage dip along the long line already had so much reduced the voltage from 230. And if they start the pumps, it goes down to 203 volts, which is too low. And the minimum voltage which the pumps were allowing was 207 volts. So even every time they started and the voltage was a bit too low, they stopped working and somebody had to go there to restart them and cancel the failure. Afterwards, you see here in the 10 minimum average values, it's more or less a higher level on the voltage, but it dips down all the time. So for a lot in 10-minute average values shows you also values which have to be an average this 10 minutes long there, and it also drops down more or less to 203 volts. After the installation of our system, we raised the set point to 233 volts, and you see you have a stable voltage because the 10-minute average values, they can't go that deep, because if it's for long term, the voltage going down, we regulate it up. That's how we could solve it, and the pumps are working through. The people on the field don't have to go there, and they save a lot of time and effort to solve these problems. The stability is given there, and if the voltage is increased, you have far fewer service calls. The only way to solve this issue on this side would be to reinforce the cables or the lines. So if you can imagine, for such long lines, to renew it, and then you're not even sure if it solves the problem for the whole time. Now in some years somebody will have the idea that everywhere has to be e-mobility charging station, so then you have to renew it again, or you have to make different ways. So for now, our system is the best solution because it was easy to install. It's solved the problem, and if the current is not too high, so what Stefan told you in the beginning, that normally the current is never a problem, it's more or less the voltage. Then you don't have to reinforce the cabling or a new transformer. You can solve it with our LVRSys. So in the end, now we're coming to the conclusion, and we hope to have some questions from your side. I will hand over for Stefan. Thank you so far.
Yeah, thank you for your attention. So to come to the summary and the conclusion. So you've seen that we are coming from the product range for utilities, for power utilities, but we are seeing more and more industrial customers which are having the same issues like the utilities, because utilities are more allowed to give up the voltage fluctuations to their customer because of the high penetration of photovoltaic devices and wind turbines and something, the new stories. And now more and more industrial customers will having voltage fluctuations. And for the voltage fluctuations, we are prepared. And the voltage fluctuations means we can reduce the energy consumptions, we can higher the lifetime. These effects are already there, so that we can do. For the voltage dips and sags, of course, we know that is also a story about for you industry customers. So therefore we have limit use, we have to say. And of course also to make a border, so we are not a reactive power compensation system. But we are sure that there are a lot of stories for industrial customers which could be done and solved with our system, because we have a lot of competitors which they are doing just the same with their kind of disadvantages they have, and we have a lot of advantages. And that means so we are looking forward to meet you as industrial customers and to get in contact with your applications, your requirements, and then we will see what we can do for you. And as Thomas mentioned, so now we're looking forward to answer your questions, and we do it like I will answer the first question, Thomas the second one, and so on and so on. And I see there is a question: how much time will take to normalize the voltage if voltage dip is 40%? So I do the example with the 20% system. So if the voltage dip is 40%, that means the rest of the voltage is 60%. And if the rest of the voltage is 60% and we hire the 60% rest voltage with 20%, so then it means we reach 72%, not more. And then the voltage then goes back whenever it comes back. So it means it's not ours, so we cannot help to bring it back to the nominal point. So then the voltage dip has to be to come to an end.
Do you have a comparison advantage, disadvantage to a classical tap changer application on the auxiliary transformer on the power plant or syscon station, as well, for example, cost comparison, THD level, etc. So for this classical application of the auxiliary transformer, we have now recently quite a lot of applications, and the main advantage for this point is that we can regulate the voltage within 30 milliseconds, and our system is maintenance free. So the tap changer is normally has moving parts, so they can get a lifetime, and so that's I would say the main advantages. And example costs, I don't know if we have it. I don't have them. THD level, it means the harmonic distortion. So our system makes no distortion, so it's for the we make no harmonic effects because we just switch the transformers on and off. So they have no harmonic distortion, but also the tap changer, I think they have no harmonic distortion. And yeah, you can add anything?
Yes. So it's the topic. So we do not have and higher the THD level. The reason is we are not using the thyristors as an inverter. So we are using, as Thomas mentioned, the thyristors like a mechanical conductor to switch it on and off. And if the thyristors are fired on, they are on, not in a frequency rate with 20 or 10 kilohertz or something. So it's just to be switched on. And if you're generating the next step, so we will step the next thyristors on. And the cost comparison to transformer, controllable transformer is, we expect we are more or less the same, but we have another advantage. So we can balance the three-phase system. So that's not possible with a normal transformer, with a controllable transformer. And the controllable transformer also a lot of maintenance. So you cannot expect, if the voltage fluctuation is there on the secondary side, and we have some applications, especially in the HVDC area, that the voltage fluctuation for the self-consumption is really high. And if you have a really high voltage fluctuation, the system runs very often and steps up and down very often. And that means it's a lifetime issue. And it's becoming a lifetime issue with a lot of advantages compared to controllable distribution transformer at this time. So next question is, as there are also more problems on the medium voltage grids, are you preparing solutions like the LVRSys also for these applications? So that means if we plan to build up systems for the medium voltage, so at the moment we don't, because we see for us as Eberle, we are not the biggest company, and for us as Eberle, we see there is a really huge upcoming market in the low voltage sector. And of course, our development parts and our improvements are going all of this kind in the low voltage level. If we will find some more, let me say, stuff, we have more ideas than we can develop at the moment. So therefore, this year, the next year, we can say we offer just systems in the low voltage sector.
Next question, is this device functional in the 3P 3V delta system? So I don't know what it is. Do you know?
Yes. For us, the three-phase system doesn't matter. So also we have systems also in the low voltage level in TT issues. So just three-phase, not a star point. Not a fixed star point from the transformer. We also have systems in the field where we have our own star point creator, because we are always controlled to the neutral point. And if we do not have a neutral point because of the grid, because it's just a three-phase grid without the PE or N connection, so then we create our star point by ourselves.
In your regulator system, which technologies use for voltage injection absorption, like battery or capacitor? So for our system, for the voltage injection, I think you mean the regulation of the voltage. We use our transformers, and we have no batteries and capacitors like you maybe have seen from UPS systems, which have two inverters to control the voltage. So our system is based on thyristors, which switch on the transformers.
So that's the reason why we do not have a huge influence to the voltage dips, because if the voltage dip is really huge, so that means there is missing energy in the complete system. And if this energy is missed in the complete system, that means we have to buffer the energy to compensate such voltage dips. And that's the reason we have less effect. We do not have any kind of a buffer, energy buffer, no capacitor, no batteries like that.
So that was the last question for now. So feel free to give us any more questions, or if not, we would say thank you for your attention. And yeah, if afterwards there are any more questions, feel free to contact us. Otherwise, you will get the information from our colleague tomorrow, and also the link to this video. You can share with your colleagues which have no time to get in time here. And then, yeah, from my side, thank you.
Yeah, thank you very much for your attention. So we'll see what we can do for you. So keep in contact. So have a nice day worldwide, and see you. Bye bye.
Bye bye.